A novel transistor designed to resemble the human brain is capable of emulating human intelligence. This transistor showcases energy-efficient associative learning capabilities, all while operating at room temperature. Greetings to everyone. Today's video focuses on the groundbreaking work of researchers from Northwestern University, Boston College, and the Massachusetts Institute of Technology. They have successfully developed a synaptic transistor that closely imitates the functionality of the human brain. This remarkable device not only processes and stores information simultaneously, but also possesses the ability for associative learning. What sets this transistor apart from previous brain-like computing devices is its stability at room temperature, rapid processing speeds, minimal energy consumption, and the ability to retain stored information even without power. The researchers achieved this feat by combining bilayer graphene and hexagonal boron nitride, creating a moire pattern that resulted in distinct electronic properties within each graphene layer. The findings of this groundbreaking study will soon be published in the prestigious journal Nature. Without further delay, let us delve into our discussion. Researchers have successfully created a synaptic transistor that exhibits advanced cognitive capabilities, drawing inspiration from the complexities of the human brain. Developed collaboratively by scientists from Northwestern University, Boston College, and the Massachusetts Institute of Technology, MIT, this groundbreaking device possesses the remarkable ability to process and retain information in a manner akin to the human brain. Through recent experiments, the researchers showcased the transistor's advanced capabilities, surpassing basic machine learning functions to effectively categorize data and exhibit associative learning. While past research has utilized comparable approaches to create computing devices that resemble the human brain, those transistors are incapable of operating at temperatures other than cryogenic. In contrast, the recently developed device remains stable even at room temperatures. Furthermore, it boasts high-speed functionality, minimal energy consumption, and the ability to retain stored information even in the absence of power, rendering it exceptionally well-suited for practical applications. The findings of the study are set to be released in the esteemed journal Nature on Wednesday, December 20th. According to Mark C. Hersam, a researcher at Northwestern who co-led the study, the brain possesses a fundamentally distinct structure compared to that of a digital computer. When it comes to digital computers, data must constantly travel between a microprocessor and memory, which not only consumes a significant amount of energy but also creates a bottleneck when attempting to multitask. However, the brain operates differently by integrating memory and information processing in the same location, leading to a much higher level of energy efficiency. In an effort to closely emulate the brain, our synaptic transistor achieves a similar capacity for simultaneous memory and information processing. At Northwestern University's McCormick School of Engineering, Dr. Hersam holds the esteemed position of Walter P. Murphy, Professor of Materials Science and Engineering. Additionally, he serves as the chair of the Department of Materials Science and Engineering, as well as the director of the Materials Research Science and Engineering Center. Dr. Hersam is also a valued member of the International Institute for Nanotechnology. Collaborating on this research endeavor were Chiong Ma from Boston College and Pablo Jarillo Herrero from MIT, alongside Dr. Hersam. The drive to create computers that mimic human brain function has been propelled by recent advancements in artificial intelligence, AI. Traditional digital computing systems, which have distinct processing and storage components, consume significant amounts of energy when handling data-intensive tasks. As smart devices continue to amass massive amounts of data, researchers are racing to discover innovative approaches to processing this information without exponentially increasing power consumption. The most advanced technology currently available for integrated processing and memory functions is the memory store. However, memory stores still encounter the drawback of energy-intensive switching. According to Hersam, the prevailing approach in electronics over the past few decades has been to construct all components using transistors and adhere to the silicon architecture. By continuously increasing the number of transistors in integrated circuits, considerable advancements have been achieved. Undeniably, this strategy has proven successful, although it comes with the drawback of consuming substantial amounts of power, particularly in the current age of extensive data where digital computing is poised to strain the power grid. Consequently, there is a pressing need to reconsider the design of computing hardware, especially when it comes to tasks related to artificial intelligence and machine learning. In order to reconsider this established framework, Hersam and his research team delved into recent developments in the field of Moira patterns, which are intricate designs that result from layering two patterns on top of each other. By stacking two-dimensional materials, novel characteristics arise that are absent in a single layer. Furthermore, when these layers are intentionally twisted to create a moire pattern, it unlocks unparalleled control over the electronic properties. In the development of the latest device, a combination of bilayer graphene and hexagonal boron nitride, both atomically thin materials, was employed by the researchers. Through intentional stacking and twisting, these materials created a distinct moire pattern. By adjusting the rotation of one layer in relation to the other, the researchers were able to achieve varying electronic properties within each graphene layer, despite their extremely close proximity at the atomic level. Harnessing the principles of Moire physics, the researchers successfully achieved neuromorphic functionality at room temperature by carefully selecting the optimal twist. Hersam noted that the incorporation of twist as a fresh element in the design process leads to an extensive array of possibilities. He explained that while graphene and hexagonal boron nitride share structural similarities, their subtle differences result in the creation of remarkably robust moire effects. Hersam and his team conducted experiments to assess the functionality of the transistor by teaching it to identify patterns that were similar, yet not identical. Recently, Hersam unveiled a cutting-edge nanoelectronic device that efficiently analyzes and classifies data. However, his latest creation, the synaptic transistor, propels machine learning and artificial intelligence to an even greater level. Hersam expressed that if artificial intelligence is designed to imitate human cognition, a fundamental task would involve categorizing data, essentially organizing it into distinct groups. However, the objective is to propel AI technology towards more sophisticated forms of thinking. Presently, existing AI algorithms struggle to navigate complex real-world scenarios, prompting the team to subject their new devices to intricate conditions in order to validate their advanced capabilities. The initial step taken by the researchers involved presenting the device with a specific pattern, namely 000, a sequence of 3 zeros. Following this, they instructed the AI to recognize comparable patterns such as 111 or 101. According to Hersam, if the AI was trained to identify 000 and then presented with 111 and 101, it would understand that 111 bears a closer resemblance to 000 than 101. Although 000 and 111 are not identical, they both consist of 3 consecutive digits. This ability to recognize similarity represents a more advanced cognitive process known as associative learning. Through experimental trials, the innovative synaptic transistor exhibited its remarkable ability to identify comparable patterns, effectively showcasing its associative memory. Remarkably, even when presented with incomplete patterns, the transistor continued to exhibit its proficiency in associative learning, proving its adaptability and resilience. In certain situations, current AI can be prone to confusion, leading to significant issues, stated Hersam. Consider the scenario of relying on a self-driving car during worsening weather conditions. The vehicle may struggle to accurately analyze complex sensor data, unlike a human driver. However, even when we provided our transistor with flawed input, it still managed to correctly identify the appropriate response. The National Science Foundation played a crucial role in providing primary support for the study titled Moire Synaptic Transistor with Room Temperature Neuromorphic Functionality. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.